Today in pre-cal we talked about the exponential and logarithmic models. These are some application problems that I want to cover with you. At the same time, they're very complex, so we're not going to go into too much depth. You will not be tested on this, but it is good information for your future, depending on what fields you might want to go in. That delves in math. These are some of the things that might apply. So the first example is about a research experiment of a population of fruit flies and increasing or according to the law of exponential growth, which is that y equals a e to the bx. That should look familiar to you from p e to the rt. And it tells us that after 2 days there are 100 flies, and after 4 days there are 300 flies. We want to know how many flies after 5 days. So we have some values. We know that when x equals 2, y equals 100. When x equals 4, y equals 300. And we want to figure out by the end, when x equals 5, what does y equal? So this is kind of a complex process that we're going to do right here. And the first thing we want to do is to develop a model or an equation that we can plug 5 into. So that's going to be the more difficult part of this. Starting with this model, I have an x and y value, and then I also have the variables a and b. I'm going to use that I have 2 sets of data to eliminate one variable, get an answer for b, then get an answer for a, get a whole model, and plug in for x. So to do that, we're just going to start with x equals 2 and y equals 100 and plug it in here. So we'll say 100 equals a e to the 2b, excuse me, because 2 is our x value. We want to get a by itself, so we're going to divide both sides by e to the 2b. And those values will cancel. And my a will be equal to 100 e over e to the 2b. Now I can go back to my original model, put that a value here, which is this whole thing, plug in my new x and y, which are 4 and 300, and go from there. So I'll have 300 equals 100 over e to the 2b, because that's what a is, times e to the 4b, because 4 is our new x value. Now, I want to simplify. I can get everything in terms of b. So I'm going to put this over 1, so that I can multiply straight across. 100 times e to the 4b is 100 e to the 4b. E to the 2b times 1 is e to the 2b. That's all equal to 300 still. Right here I can reduce this by doing 4b minus 2b, which is 2b. So I have 100 e to the 2b equals 300. I want to get the e by itself so that I can start to solve for b. So I'm going to divide both sides by 100. Let those cancel, and 3 will be equal to e to the 2b. To get rid of the e, I'm going to take the natural log of both sides so that that will cancel, and I'll have that the natural log of 3 equals 2b. I almost have b by itself. To get it there, I'm going to divide both sides by 2, and I will find in my calculator that b is equal to 0.549. If you had any trouble here, it might have been that you just forgot to put this, close the parentheses here, and then do divided by 2. But that's your value for b. Now I can get the value for a, because a equals 100 over e to the 2b. So I can do 100 over e to the 2, and instead of b, plug in 0.549. If I put that in my calculator, my value for a is 33.4. And that is with some rounding there. Now I have a and b, so my overall model is y equals 33.4 e to the 0.549 times x. Now I have a model in terms of x and y, so that somebody could plug any x value in and get out a y value. Now, we talked a lot in class about a lot of different things within this idea, but we also covered that up until now in your previous math life, most of the time somebody else has given you a formula and just told you to plug in and find an answer. Somebody had to make up that formula. It didn't come from nowhere. They used some information just like we just did, and they used the fact that they knew the general model to figure out what would describe that information and most closely relate it so that you could make some predictions and estimations. And that's exactly what we've done here. See that it is a long process, so maybe that will make you appreciate the formulas when you're given more often. Now all we want to do is figure out how many flies there will be after 5 days. So I'm going to say y equals 33.4 e to the 0.549 times 5. If I put all of that in my calculator, I will get that y equals 519. Therefore, there are about 519 flies after 5 days. in one of the classes today, we were pretty curious about what would happen as time went on. So we also tried plugging in 50, and there were millions of billions. So there was like 13 zeros on that, which would be pretty huge if we could see that many flies in this situation. So the reason that somebody might care about fruit flies, if I was a crop grower and the flies were getting to my fruit and killing my crop, that would be pretty important to me because that would be my way of life. So that's one application. The next application we're looking at is carbon dating. And carbon dating deals with fossils. So this might be something an archaeologist might be interested in. Someone who deals with something to that effect. Because in living organic material, the ratio of the number of radioactive carbon isotopes, carbon-14, to the number of non-radioactive carbon isotopes, carbon-12, is about 1 to 10 to the 12th. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t in years. There's the formula that somebody else has developed to model this behavior. Now we're going to estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 over 10 to the 12th. Okay, to do that, we were given the R, we were given the formula, we just have to plug in and solve. So 1 over 10 to the 13th power is equal to 1 over 10 to the 12th power times e to the negative t over 8,223. First, we want to get e by itself. So to get rid of this, we're going to multiply both sides by 10 to the 12th. This will cancel, and I have e to the negative t over 8,223 equaling 10 to the 12th over 10 to the 13th. Now, if I reduce this right here, I will get 1 over 10. And that's because 13 minus 12 is 1, and so it'll be 10 to the first on the bottom. That's a power of exponents rule. Now I've got e by itself, so I can take the natural log of both sides to get that to cancel. And I'll have natural log of 1/10 is equal to negative t over 8,223. To get t by itself, I'm going to multiply by 8,223 and the negative form of that so that I can get rid of the negative as well. And t will equal whatever this is. If I go ahead and plug that into my calculator, I will get 18,934. So it's about 18,900 years old. So I'm going to write my sentence. The fossil is about 19,000 years old. And again, that's an estimation. Okay, this would be a more exact number, so with the decimal points that went with it. But we talked today about how decimal points in this case wouldn't be as important because we're talking about months over 19,000 years ago. So unless we were looking for something very specific, we would know that if we were the archaeologist. We could kind of estimate how old something was. Also, these models are a generalization of behavior. It's not necessarily exact. So that's important to realize. The next example I think will speak to you and your place in life, and that is about college and viruses. This was probably the most interesting to most students today. On a college campus of 5,000, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this function, where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. The first thing we want to do is to see how many students are infected after 5 days, and the second is how many days will it take to cancel class. So the reason this is important, and I'm not going to go into too much detail here, but we did go into more in class, was that students live in dorms, which are close quarter living. They share things. They don't always live a healthy lifestyle that would keep a good immune system up. They may not have insurance, so they may not go to the doctor as often. And then they go to classes and Starbucks and study places where there are lots of people that are exchanging things. They go back to close living, and viruses spread very quickly in a situation like this. And that's true of all types of viruses. In this case, we're just talking about the flu. Part A was to figure out how many after 5 days. So we're going to use the model, and we're going to plug in 5 for t. We'll put all of that into our calculator, and after 5 days, one student has spread now to 54 students. You're going to be amazed when we see what happens for the campus to close down. So part B is to close the campus. If there are 5,000 students that attend this school and 40% have to be sick, we're going to multiply by 0.40 because that's how we make that a decimal. That means about 2,000 of the students have to be sick for them to close classes. Now the reason they would close classes is so that people would not meet as often. They might go home and have their parents take care of them or go to the doctor. They might get some rest, and that can help maybe not stop the virus but slow it down significantly. If they don't, they would have an epidemic, and that would be out of control. That would be a problem. People can't do well when they're that sick. So let's figure out when that's going to happen for this particular school. If I make my y value 2,000 and leave the t this time because I want to figure out how long, which would be the time factor, I want to get t by itself. To do that, I've got a lot of steps, especially since this is within an exponential, under a fraction, in an exponent. So I'm going to put this side over 1. I'm going to cross multiply so that 5,000 will equal 2,000 times 1 plus 4999 e to the negative 0.8t. I'm going to divide both sides by 2,000. Oops, I shouldn't have canceled that. I just wanted to reduce it. Anyways, it is 2.5 as a decimal, equals 1 plus all of this business again. I'm going to subtract 1 from both sides. Again, my goal is to get t by itself. So I have 1.5 plus 4999 e to the negative 0.8t. Divide both sides by 4,999. It's important for me to note here that this right here, if I put it into my calculator, would be a very small fraction. And I don't want to do that because it won't be as precise when I round. So I'm going to leave it like this. I'm not going to reduce it here. Now I have e by itself, so I'm going to take the natural log of both sides. That cancels. The final step will be to divide by negative 0.8. All of this by negative 0.8. And that will equal my time. Now when I put this in my calculator, I want to be sure I use my parentheses correctly, or else that could be a major problem. And in this case, the time ends up being 10.1 or so. So in 10 days, 2,000 or more students will have this virus. Think about the implications there, guys. In 5 days, it was only 50. Started out as 1. 5 days, it was 50. 5 days later, in 10 days, it was 2,000 students. So that's why this is so important to study, especially when we are talking about the medical field. The very last example that we covered was dealing with earthquakes and their magnitude, talking about the Richter scale. In particular, on the Richter scale, the magnitude R of an earthquake of intensity I is given by R is equal to log of I over I naught, where I naught is 1 is the minimum intensity used for comparison. Find the intensities per unit of area for each earthquake. Intensity is a measure of the wave energy of an earthquake. The first one we're talking about is in the northern Sumatra in 2004. This really did happen. This was a registered earthquake at 9.0. One of the worst that has ever been registered. The northern Sumatra is in Africa and on that continent, so that's what we're talking about here. We're going to plug in that R equals 9, and then we're going to take the log of I, and I'm not including I naught because I naught was 1, so I over 1 is just I. To get I by itself, I'm going to raise both by the power of 10. This one will cancel, and 10 to the 9th power is like saying 9 zeros. So that's pretty intense, right? And that's just the unit of area. Remember, we're talking about the wave energy. Okay. Let's look in contrast at the one that hit southeastern Alaska in 2004, same year, but with a magnitude of 6.8. Again, to get I by itself, we're going to raise both by the power of 10, and 10 to the 6.8 means the intensity was 6,309,573. Notice from here to here, I started with 9 and went to 6.8, which is not that drastic of a drop, but the intensity is. Okay, this is in the millions, this one is in the billions. So that's pretty different there, and that's why we use the logarithmic scale to show that. This was still a pretty intense earthquake, but this one would have been like total devastation. And that was the topic for today. There is no assignment that goes with this. It's just good information for you to know how to do and have some familiarity of it. So I will see you when you return to class.